Hello everyone, my name is Peixuan. Let me introduce our work at New York University, collaborate with Fudan University, Sifter, and Inversion-Free large capacity programmable package scheduler. The outline of my presentation starts with the background and motivation. I will introduce an interesting observation and insights which facilitate our design, Sifter. And then I will present our evaluation and implementation, and we come to the conclusion. Let's start with the background and motivation. The motivation here is the emerging delay-sensitive applications which have hard deadline requirements. For example, the remote surgery and the V2X. I guess you don't expect the remote surgery packets being delayed by the actual delay, and the doctor in the remote have some trouble to applying their operations. So this application relies on the accurate packet schedulers, which can guarantee the deadline to deliver each packet. We have a bunch of different scheduling goals here, including the minimizing the average flow completion time, bandwidth allocation among different flows, do the flow isolation between different network slicings, as well as others like delay guarantee and the time-sensitive networking. The academia have come with a variety of different scheduling algorithms to fulfill all these requirements. Some of them in the category to provide the minimized flow completion time as well as the weighted bandwidth allocation. This algorithm can tolerate slight skew on the packet serving order. In other words, some approximate scheduler can fulfill their requirements. A slightly scheduling error don't harm their scheduling goals. However, for other delay-sensitive applications, the scheduling order is kind of harsh on their accuracy. So in those cases, we might use the accurate schedulers like PIFO. However, PIFO has their own limitations. They're expensive and they're hard to scale. So we want accurate packet schedulers which can support large capacity as well as high accuracy. For example, in this V2X application, let's assume these red packets are from the V2X application. And the rank here denotes their scheduling order. If we have an approximate scheduling scheduler, then they can introduce some scheduling error, which means some packets with a larger rank would dequeue prior than the other packets with smaller ranks. And this packet can introduce extra delay and can be critical to this application, such as the self-driving cars. So to understand why we have these inversions, we need to look into how does the approximate packet scheduler implement. The majority of the approximate packet scheduler are implemented based on the FIFO. So in other words, each queue here is a FIFO queue, and the packets comes in the first in, first out. Since the first in, first out scheduling scheme, we can see that the packet dequeuing ordering are fully dependent on their inqueuing ordering. So in this case, a packet with a rank 3 is leaving prior than another packet with rank 2. So this can cause the packet inversion. All the packets within the same FIFO are subject to these inversions caused by the first in, first out queue. And to eliminate such inversion, the solution is pretty intuitive. If we can sort the packets before we dequeue them, we can eliminate those packet inversions. So a mini PIFO can come into play to sort all these packets. Let's say we have the time to sort all these packets before we dequeue them. There will be no packet inversions. But actually, sorting takes time, and we don't have this time to keep up with the line rate. This brings us to our observation of the speed-up factor. Actually, we found that to manipulate a metadata or a descriptor in the memory takes much less time to transmit a full packet on the output link. And the definition of this speed-up factor is the time to transmit a packet on the output link divided by the time to move a metadata. For this example, we have the speed-up factor of a little bit above 10. This means during the time when we are transmitting a packet to the output link, we can kind of process 10 metadata in the scheduler. In other words, we can sort 10 metadata in the scheduler. So this will bring us time to sort the packet before we are dequeuing them. If we know the packet to dequeue at the current time, then during the time to dequeue this packet with the smallest rank, we can sort the packets in the next available FIFO. This brings us to the design of our scheduler, Sifter. The architecture of the Sifter mainly composed by two major components. The first part is a mini PIFO, which stores the packet with the smallest ranks in the scheduler, also do the sorting. And the other component is the FIFO-based rotating calendar queue, which you use the multiple FIFOs to do the coarse sorting of the packets with larger ranks, while providing a fairly large capacity because of the implementation based on the FIFO. And we have the statement that we always occupy the mini PIFO by a certain number of packets, so that we always have enough packets to dequeue when we are trying to sort the packets in the next available FIFO. Thus, we introduce a sifting threshold, which means we always keep the mini PIFO to occupy by this level. The operation of Sifter consider three different operations. The enqueue is fairly straightforward. When the packet comes in, we check its rank. If it is small enough, we directly put it into the mini PIFO. We have this Senatel to serve as a threshold to see whether a packet's rank is small enough to directly go into the mini PIFO, or it has a fairly large rank that should be coarsely sorted in the FIFO-based RC queue. This Senatel value is usually represent the smallest rank in the RC queue, which can support the statement that the mini PIFO always holds the smallest ranks packets in the scheduler. The dequeue operation is even more straightforward. Since the mini PIFO always holds the packet with the smallest rank in the scheduler, then it's always safe to dequeue from the head of the mini PIFO. And the magic actually happens in the sifting process. When the occupancy of the mini PIFO is lower than the threshold, the sifting process starts. It will find the next available FIFO in the RC queue, try to traverse through all the packets in that FIFO, enqueue them into the mini PIFO. Upon this traversal, all the packets with the smaller ranks will stay in the mini PIFO, and the packets with relative larger ranks will be kicked back to the RC queue. So it's just like we're sifting the sands. The smaller sands will be stay in the mini PIFO. And let me briefly introduce the condition of the inversion-free. So basic idea here is we want to guarantee we have enough packets to dequeue during the time when we are trying to sort the next available FIFO. So the first condition is the time to drain the mini PIFO should be larger or equal than the time to traverse the next available FIFO. This means the threshold times the speedup factor is larger or equal than the size of the FIFO in the RC queue. The other condition is after we refill the mini PIFO, the refilled packet should bring enough time for the next sifting process. This means the size of the whole mini PIFO minus the threshold, this is the reloaded metadata number, should be larger or equal than the threshold of the mini PIFO. That is the minimum metadata we want to keep in the mini PIFO. And let me introduce the evaluation and implementations in our project. The evaluation, we have two major parts of evaluation. The first part is the packet-based simulation on the NF3. The other part is FPGA-based hardware prototype we evaluate on a hardware testbed. For the NF3, we start with the single node flow convergence. We deploy this simulation on a star topology with one congestion point. We trying to do a fair bandwidth allocation among 8 different flows, join and leave at different time. According to the evaluation result, we can see that Sifter can achieve nearly identical flow convergence performance as an ideal PIFO, while the other approximate package schedulers such as Programmable Canada Q and SB-PIFO would subject to some fluctuation on their bandwidth due to their approximation and scheduling errors. And we also extend our evaluation into a larger scale factory topology. So we extend our topology with 256 hosts with more than 500 flows in our simulation. We can see that in both flow completion time as well as the end-to-end delay, the Sifter can achieve a nearly identical performance as an ideal PIFO. We also implement our Sifter on the FPGA and deploy it in our hardware testbed. We use the Pika file to generate the packet descriptor as the input, and we use rate control to represent the input rate and output rate of the 100 gigabits per second line rate. We feed the packet descriptor into the Sifter FPGA implementation and collect output trace of the descriptor. From the result of the throughput, we can see that the Sifter prototype can reach 100 gigabits per second with both fixed packet size as well as the varying packet sizes. Also, we check the scheduling order of the packet descriptors we collect. We see the ranks in the packet descriptor are in the monotonically increasing trend, which means there are no inversions in our packet scheduling process. So let's come to the conclusion of this presentation. This presentation, I introduced Sifter, an inversion-free and large capacity programmable packet scheduler. Sifter can serve as a generic inversion-free programmable packet scheduler, just like the PIFO does. And it combines the advantage of a PIFO and a FIFO-based scheduler. It has the advantage of inversion-free like PIFO does, and it also supports a large capacity like the FIFO-based approximate packet schedulers. We apply a two-step sifting sorting with the mini PIFO. Basically, we first do a coarse sorting with the FIFOs and then do a fine-grained sorting with the mini PIFO. And we can support a large capacity because of our FIFO-based implementation. The in-queue and DQ operation is only 0.1 complexity, so we can support fast scheduling process to make it able to cope with ultra-high line rate. Thank you for listening.